On the way we go. Okay, so I seem to be on every big, like, Navy-funded field experiment. I'm always the token theoretician, and in this class, I'm the token definition guy. So I get all the lectures for basic definitions. So today we're going to now, after having defined radiometric properties this morning, we're going to define these apparent optical properties that you've been hearing about. And then Emmanuel made me put in a section on what's called the BRDF, which is important, but I have a feeling that by the time 6 o'clock rolls around, we won't make it today, but somewhere along the way, you'll learn what Lambertian reflectors are. Okay, so back to the organization chart. We talked about radiance and how these irradiances are defined and measured this morning. You've now measured a bunch of these things out on the dock today. So this lecture is down here in this box called apparent optical properties. And as we've emphasized, inherent optical properties are properties of the medium. They don't depend on the ambient light field. Apparent optical properties, or AOPs, are things that depend on the IOPs, but they also depend on the radiance distribution. So they're partly IOP, partly radiometric. And the thing you're going for is something that you can measure easily with optics, but you can relate it back to what you're really interested in, which is IOPs. And the thing you need is that whatever this thing is, and there's a bunch of them, that they display enough stability to be useful for approximately describing the optical properties of the water body. That's the half of the definition that everybody forgets. So, first of all, because AOPs depend on the ambient radiance distribution, you cannot measure them in the lab or on a water sample. You have to go out in nature and measure them with whatever sky and in-water radiance distribution is there at the moment. And whatever it is has to have stability. So think of an irradiance. Okay, an irradiance depends on the AOPs. It depends on the ambient radiance distribution. Well, is that an AOP? It only satisfies the first half of the definition. There's no stability in an irradiance because you go out, it's sunny, you measure the irradiance, here it is. 5 minutes later, cloud goes over the sky, you measure the irradiance, it's an order of magnitude less. So irradiances are very sensitive to things like sun angle and sky conditions. So they don't meet the second half of the definition. And if you don't remember anything else out of today's lecture, remember that radiance and irradiances are not AOPs. They don't have regularity or stability. And there are a lot of people in the field seem to think that everything is either an IOP or an AOP. It's not. Some things are IOPs, some things are AOPs, and some things are radiometric variables. They're neither one. Okay. So the idea of having a good AOP is that it will depend weakly on the external environment. So things like sun angle, sky condition, surface waves, but it will depend strongly on the water IOPs, which are what we are really after. And these things are usually either ratios of radiometric variables or their depth derivatives, normalized depth derivatives of radiometric variables. And we're going to look at about a half a dozen of these now. And the reason these things kind of came into use was that in the old days you didn't have ACSs and all these other instruments. So IOPs were hard to measure, but if you did know them, they're easy to interpret. But AOPs were easy to measure, but the problem is they're sometimes hard to interpret. So that's my law of conservation of misery. It's either easy to measure, hard to make sense of it, or it's hard to measure, but it's easy to make sense of it. And this is less true today. We now have a lot of instruments that you can measure IOPs and you're good to go. But AOPs are still the basis of remote sensing, for example. Okay, so in a perfect world, we'd have this instrument, we'd stick it in the water, and you'd just measure the full radiance distribution. And you're done, because that tells you everything about the light field. And you would measure the absorption coefficient and the volume scattering function. And those are, of course, going to be functions of position, time, wavelength, and scattering angle over here. But you'd measure those things, and you know everything about everything about the optical properties of the medium. So you're done. You don't have to measure backscatter and beam attenuation and all those things. If you wanted to know those, you just compute them from these two IOPs. And here, if you measured the radiance, you're done. If you then decide you want to know what the irradiance is, you wouldn't have to measure it, you'd just compute it from the radiance. And so nothing else would be needed except these things. But of course the world isn't perfect. So radiance is difficult to measure, time consuming, and most of all, if you measure the full radiance distribution, you probably don't need all that information anyway. There are some problems where you really need to know the full radiance distribution, but usually just knowing, for example, scalar irradiance is all you need to do to grow phytoplankton and heat water. And so anyway, the idea is let's find simple measures of the light field that are simpler than measuring the full radiance distribution, but which are also useful for describing the optical characteristics of the water body. Okay, so here's a plot, for example, of ED and EU. Now, this is just really from a hydrolyte run where I picked case 1 water, I plugged in a chlorophyll, I plugged in some sun angles, I had a clear sky, I had a solid overcast sky. I just did some hydrolyte runs, and I plotted ED as the solid curves and EU the dotted curves. And so here's sun is straight overhead, 30, 60 degrees, and then an overcast sky. Well, notice if you look at going from the sun straight overhead to an overcast sky, that's basically a factor of 10 difference in ED. So that's why an irradiance really can't be related directly to what's going on in the water, because it's really very sensitive to sky conditions and sun angle. But you look at this and you say, well, you know, wait a minute here. Look at the slopes here. They're all kind of similar. The magnitude is shifted by an order of magnitude by the sun angle, but these all have pretty much the same slope. Or same thing on EU. They're shifted by the same order of magnitude, but once again the slopes are they're not identical, but they're sort of close to it. So you think, well, maybe looking at the slope of the ED as it decays with depth, maybe that's not too sensitive to sun angle, but it will be sensitive to the IOPs. So that gives you the idea of, let's look at the depth derivative of the irradiance normalized by the irradiance. So 1 over ED, dE, this of course is just derivative of the log of EZ. So this is sometimes you'll see that KD is the log derivative of ED. And really what we're saying is when we normalize this, if you multiply, the sun goes behind the cloud, ED will change by a factor of 10, but that factor of 10 will cancel out between here and here. And so we're really just looking at the slope of the curve. And then you can do the same kind of definition for EU and L and any other radiometric variable, and you get different functions. So there will be a KD for the rate of change of ED with depth, a KU for how EU changes, a K for LU for upwelling radiance, a K for scalar irradiance, and in principle those are all going to be something different. Okay, so here's just a plot for some different Ks. So once again, this is the case 1 water, chlorophyll of 1. I put the sun at 0, the solid curves, and the sun at 60 with the dotted curves. And then the different colors are KD, KU, K0, KLU, etc. Well, you know, there's a good bit of variability there. So over here we're maybe at 0.7 or 0.6, but out here we're at 0.12. So there's quite a bit of variability there. And the variability is greatest near the surface. You can see the curves are kind of coming together with depth, and here at 50 meters there's very little difference in the different K functions, but at the surface it's sort of a factor of 2. Here's another plot where I put the chlorophyll of 5. So once again there's kind of factor of 2 variability at the surface, but down by about 20 or 25 meters they've all come together, and then they're all basically the same. And so what you're seeing here is what's called the asymptotic radiance distribution developing. Near the surface, the sun's over here, it gets in the water, and you get a particular value for a KD or a K0 or KLU. But as you go down in the water, scattering basically takes that collimated solar beam and scatters it around to where if you were at 30 meters in this water and you look around, all you can say is that it's brightest looking straight up. It's not as bright in that direction, and it's less bright in that direction. But you can't see where the sun was in the sky. So over here in this one, maybe you have to go to 75 meters or something. But the idea is that all of these AOPs will be different near the surface because they depend on things like solar angle a little bit. And remember, a factor of 2 here is better than a factor of 10 for ED, for example. But if you go deeper into the water, they all become the same, and they become actually inherent optical properties. So this value here or this value here are really determined only by the IOPs. So a lot of people will try to use these things and just go deep enough to get away from the surface variability, come down to the values at say 20 or 30 meters, and then say, I now have something that's really determined by just IOPs, and I can maybe take this K value and relate it back to an IOP. Okay. So yeah, I've commented here, the asymptotic value in this case is 0.19 per meter. Over here it's 0.11, and that's determined only by the IOPs. Okay, now something to think about here is, if you look at one of these curves, I've got them plotted all the way up to the surface, and these are sort of, if you will, true KDs computed by hydrolite, where I'm using like a 1 millimeter spacing and depth in the computations and all. That's great. But in the real world, you can't measure ED right up to the surface and then measure it, every centimeter in depth. You're going to have to start at, 5 meters, 10 meters, whatever. It depends on how big the waves are. Out here today, yeah, you could measure ED from just below the surface on down with depth and really get a 2 meter waves and you're hanging over the side of the ship, you're going to have to start at maybe 5 meters. And then you're going to have some measurements down here, but you'd need to extrapolate back towards the surface, and that's a little bit iffy. So if you thought of measuring ED here, let's say starting at 5 meters, so you'd have maybe these points, but then sort of fit a curve to those and extrapolate ED back to the surface. Well, the reality is there's all kinds of waves flickering and so forth, and so it becomes pretty difficult to take data down here and then fit a curve and then extrapolate back to the surface.